thanking Janil and the organizers for the invitation. I'm glad to be here. So my talk is about geometric structures on holomorphic manifolds. And the idea will be that those rigid geometric structures on holomorphic manifolds are always symmetric enough, and one can hope to classify them. So I will give some precise definition, but let me start with two results which go toward this direction and which were a motivation for this work. So I will state a first result which deals with holomorphic foliation. This is a theorem of Higgs in the 90s about classification of codimension 1 holomorphic foliations on complex tori. So here lambda is a translation lattice in Cn with a compact quotient. And we try to understand holomorphic codimension 1 foliation without singularities of those tori. The result of Higgs says that there are two kinds of foliations. The generic foliations are the simplest one. They are given by the kernel of some holomorphic one form on the torus. Since holomorphic one form on tori are translation invariant, those foliations must be simply translation invariant foliation on Cn, which descends on the quotient. So this is the generic example of foliation. For those tori which admit fibration, you start with some linear map from Cn into C, and it could happen that this descend on a map from the torus to some elliptic curve. In this case, for those tori which admit fibrations, you can pick up a meromorphic function, non-constant meromorphic function on the elliptic curve, and then pull back by the fibration the meromorphic one form udz, where z is a global coordinate on the elliptic curve, plus some holomorphic one form on the torus, gives you this closed meromorphic one form on the torus. And one foliation can come like the kernel of this closed meromorphic one form, because it's easy to see in local coordinates that those foliation will extend through the poles of capital omega into a non-singular holomorphic foliation on the torus. So somehow you have two kinds of foliation. The generic ones are translation invariant. I say generic ones because generic tori admits algebraic dimension 0, meaning they do not admit non-constant meromorphic functions. So for generic tori, the only foliation are those which are translation invariant. For those which admit some non-constant meromorphic function, meaning that the algebraic dimension here is bigger than 1, somehow the algebraic dimension is a number of independent meromorphic functions you'll find on the manifold. Then, for those, you have these turbulent foliations, which are still very symmetric because they are symmetric by all translation in the kernel of pi. they are on the kernel of pi gives you a subtorus of codimension 1, which acts by symmetries for those foliations. Meaning somehow that the symmetry group of a foliation on a complex torus will admit a big symmetry group, codimension 1 symmetry group. And for those which are generic, they are simply translation invariant. So this is a description of this result of Gis. So the idea would be to try to understand if this kind of symmetry stands true for other holomorphic geometric structures than foliations and for other manifolds than tori. So this was the first statement, which is a motivation for what I did. And let me give you a second result, which is a generalization of a theorem of Bogomolov in the 70s for holomorphic tensors. But this result could be generalized for a broader class of geometric structures, those which I will call rigid in Gromov's sense, and will give the definition. And somehow this result of Bogomolov can be adapted to give the following statement. Let M be a complex manifold. You don't need compactness for this result. With algebraic dimension 0. Meaning that the only meromorphic functions are the constant functions. Then, any holomorphic rigid geometric structure on M is locally homogeneous away from a proper analytic subset D. So away from some analytic subset D, you are locally homogeneous on an open dense set U, which is the complementary of D. So I need to define here rigid. And maybe I will need to define locally homogeneous. This result implies that as soon as you have those kind of geometric structure on manifold with algebraic dimension 0, you will have some local symmetry for the geometric structure. Let me just begin to explain this word rigid here. So first examples are given by holomorphic Riemannian metrics, which are similar geometric structure as Riemannian metrics, but for the complex background, they are sections of the bundle of complex quadratic form in the holomorphic tangent bundle, such that in each point, the quadratic form is non-degenerate of maximal rank. If you take a Riemannian metric which is real analytic, you complexify it, you will get this kind of holomorphic Riemannian metric, the flat example being dz1 square plus dzn square. This is the flat example. So they are not Hermitian, they are holomorphic quadratic forms in the tangent bundle. As in the Riemannian setting, they will admit a unique Levi-Civita connection. which is a torsion-free connection for which this tensor is parallel. So connections, holomorphic connections in the tangent space are also rigid geometric structure. Rigid means that for a local diffeomorphism, here this would be local biholomorphism, preserving the geometric structure, this local biholomorphism is completely determined by a finite jet. This is known to be the case for Riemannian metrics, since you need to send parametrized geodesic on parametrized geodesics as soon as you know the action on the directions, the differential, you completely know the isometry of the Riemannian metric on an open set. So this means that those Riemannian metrics are rigid. Connections are rigid for the same reason. Also, conformal structures in dimension higher than 3. Holomorphic conformal structure in dimension higher than 3. So those are good examples to have in mind as rigid geometric structure. Those which are not rigid are, say, foliations or holomorphic symplectic forms or holomorphic contact forms. Here, the local group of symmetry is always of infinite dimension. So, pseudo-Kaehler, let me think. What do you mean pseudo-Kaehler? Riemannian metrics are rigid. Oh, pseudo-Riemannian are rigid, yeah. So pseudo-Riemannian are rigid, meaning that in the real case, thank you. In the real case, Lorentz metric or pseudo-Riemannian metric are rigid because they are non-degenerate. And as in the Riemannian setting, they have a Levi-Civita connection. Since the Levi-Civita connection is rigid, they are rigid. In fact, of course, I said that holomorphic Riemannian metrics are complexifications of Riemannian metrics, but you can think also as complexification of real analytic pseudo-Riemannian matrix or real analytic Lorentz. Let me go to the second definition here. For locally homogeneous, the definition is the following. On U, on the open set where the geometric structure is locally homogeneous, we have the following thing. For any point in U and any direction in U, there exists a holomorphic vector field, maybe on a smaller open set than U, which contain the point, such that at the given point, our vector field realizes V, and the flow, the local flow of this vector field preserves the geometric structure, meaning that this vector field is like a killing field for the geometric structure. Its flow preserves the geometric structure. It's like the infinitesimal version of the symmetry. Preserving such rigid geometric structure means satisfying some PDE. This PDE usually is overdetermined, so you don't have non-trivial solutions. Here, in the conclusion of the theorem, we have lots of non-trivial solutions because they span the tangent space. Somehow you can flow in any direction, preserving the geometric structure along these killing fields. Meaning that at the end, in the theorem, you have lots of those local symmetries. Morally, what will happen on the open set, the geometric situation is the following. All those local killing fields form a Lie algebra, which is of finite dimension and acts transitively on this open dense set. Morally, you can think that on this open dense set U, you have a local model for the geometric structure, which is a homogeneous space associated to the Lie algebra of symmetries. So this is what we call the GX structure in Thurston-Ehresmann sense. So on U, we get a holomorphic GX structure where G is a complex Lie group of finite dimension, and X is a homogeneous space associated to G. Once again, this G is the complex simply connected Lie group associated to the Killing algebra. The general picture here is the following. U, the open dense set, which is locally homogeneous, is identified with the homogeneous space by a map if you assume that the open set is simply connected. If not, this local identification is well defined only on the universal cover, and this is called the developing map. So you have small open sets in U, which are diffeomorphic with open sets in G over H, and the transition maps are given by the action of G. So it's a more stringent structure as that of a complex manifold. We are locally modeled on a homogeneous space, and the transition maps organized in a complex Lie group of finite dimension. The general picture is this. You have a local diffeomorphism from the universal cover to this homogeneous space, which is equivariant for the action of the fundamental group on the universal cover and on the homogeneous space through what we call the monodromy morphism, which goes from the fundamental group of the manifold into the symmetry group G. So this is the general picture of what happens when you have a manifold with a local model which is a homogeneous space. So somehow there is an open dense set in your manifold which is locally homogeneous, and the geometric structure comes from this construction where G is a G-invariant geometric structure on the homogeneous space. It's exactly like what happens in, you have this classification of the 8 locally homogeneous, the 8 Thurston geometries. So, of course, if you ask the question like this, I can answer the following. As soon as you show that, say, a holomorphic Riemannian metric is locally homogeneous on an open dense set, what you would like to prove is that, for example, this is locally homogeneous everywhere. Sorry. Of course. So the point is the following. Yeah. So I understand. So first, for local examples, if I take any real analytic Riemannian metric, I can complexify, and I will have here some coefficients. And everything happen, but what is important is that for generic coefficients, the killing algebra is trivial. You don't have any symmetry. What says this theorem is this germ of holomorphic Riemannian metric cannot be put on a manifold with algebraic dimension 0. And a consequence of this theorem, donc a corollary, in fact, is the following. Let G be a holomorphic Riemannian metric on a complex manifold with algebraic dimension 0, sorry, on a complex manifold of dimension 3 on a compact complex manifold of dimension 3, then G is locally homogeneous. So the point is very few germs of holomorphic Riemannian metrics can be put on compact manifolds. This theorem says that in dimension 3, only those which are locally homogeneous can be put on a compact manifold, and you have a GX structure where the homogeneous space is one of those which admit G-invariant holomorphic Riemannian metrics, meaning it could be the flat model, it could be the complexification of the anti-de Sitter model, like SL2 of C with the killing metric, or any homogeneous space which admit G invariant holomorphic Riemannian metric. So the point is that to go from this theorem to the theorem saying that the holomorphic Riemannian metric is locally homogeneous, there are two obstacles. The first is to show that starting with this open-dense set of local homogeneity, you can extend it to all of the manifold. When you are of algebraic dimension 0, when you are not of algebraic dimension 0, I will give you hints of why the theorem is still true. So the message here is that those holomorphic Riemannian metrics are not at all generic on compact manifolds. As soon as they are on compact manifolds, one could hope to classify them all. But there are interesting examples. Okay, so at this point, I state two theorems about geometric structure, G's theorem and this Bogomolov theorem about symmetries. The first example was about global symmetries for foliations. The second example was about local symmetries for rigid geometric structure. As foliations are not rigid, let me show how this Bogomolov theorem can give you G's result for foliation, since foliations are not rigid. So let me see some relation between these two results. So let's say like this, Bogomolov, in this context, of course, implies G's result. So you have your tori, with the foliation. The foliation is not rigid, but on the torus, you have a rigid geometric structure because the torus is an affine manifold. It means a flat affine structure. For example, you can choose the holomorphic trivialization of the tangent bundle on the torus, which is given by commuting globally defined holomorphic vector fields. So those n commuting holomorphic vector fields is a rigid geometric structure. It's a trivialization of the holomorphic tangent bundle. In particular, is a connection, a flat connection. You put together this trivialization of the holomorphic tangent bundle with any foliation. Gives you now a rigid holomorphic geometric structure. So this Gromov theory enables one to put together geometric structure if one of them is rigid. The full geometric structure is rigid because local diffeomorphism preserving both must preserve a rigid one, so they are completely determined by a finite jet. So we apply now Bogomolov theorem for this geometric structure when assuming that the algebraic dimension of the torus is 0. Means that we have lots of local symmetries for the geometric structure. We have lots of local killing fields, X, which preserves G. But a vector field preserving G must preserve both foliation and the holomorphic trivialization of the tangent bundle. In particular, X must commute with all translation on the tori. But a vector field commuting with all translation is itself a translation. Meaning that the possible killing algebra are subalgebra of translations. Since a subalgebra acts transitively, we need to have all translation in the symmetry algebra. That means that the foliation is invariant by all translation. So this theorem says that for any holomorphic geometric foliation for any dimension and any holomorphic geometric structure on a complex tori of algebraic dimension 0, this must be translation invariant. This is the relation between these two results. And in fact, if you look to the structure of the proof, this will work for any holomorphic parallelizable manifold of algebraic dimension 0. We only use the fact that there is a holomorphic parallelization of the tangent bundle, and the manifold is of algebraic dimension 0. So let's generalize this fact in the following way. So Bogomolov implies the following. For any parallelizable manifold, parallelizable manifolds are known to be quotients of complex Lie group by lattices. So if you try to understand what are those complex compact manifolds with trivial holomorphic tangent bundle, of course you have complex tori. Those are the only Kaehler examples, but you have non-Kaehler versions which are quotients of complex Lie group by a lattice. Interesting example is SL2 of C over gamma, for a lattice gamma. And those are all complex parallelizable manifolds. So most of them are of algebraic dimension 0. If P is a complex semi-simple Lie group, like SL2 or SLN of C, the only meromorphic functions on SLN of C over gamma are the constant function. So those are manifolds of algebraic dimension 0. So for any of those, for any and any G holomorphic rigid geometric structure, we have that the pullback to the universal cover of the manifold pull back the geometric structure in a right invariant geometric structure. Meaning that only those obvious geometric structures will descend on P over gamma, those right invariant geometric structures on P. Yeah, it's here, it's co-compact lattice, or at least a lattice such that the quotient is of algebraic dimension 0. But the statement works for co-compact lattice. What is important here, that the algebraic dimension of the quotient is 0, but this is realized for co-compact lattices in complex semi-simple Lie. And this gives you restriction for which holomorphic geometric structure will live on those kind of quotients. For example, give you the following restriction. This is a corollary. SLN of C over gamma with co-compact gamma do not admit complex affine structures. And this comes from the following result. Assume that there is a complex affine structure on SLN of C over gamma by contradiction. Then this will pull back on SLN in a right invariant complex affine structure. And we'll show that there are no right invariant complex affine structure on SLN of C. So this work, in fact, for any holomorphic GX structure, give a characterization of those GX structures which live on those manifolds. So any holomorphic GX structure on SLN of C over gamma pull back in a right invariant holomorphic GX structure on SLN. Meaning that the picture is the following. You have this monodromy morphism from the fundamental group of the manifold. Here, the fundamental group of the manifold is gamma into G. The monodromy group will be a morphism from the fundamental group into G. But since the geometric structure is right invariant on the SLN of C, this monodromy group will simply extend to a morphism of complex Lie group from SLN of C into G in such a way that the image acts with an open orbit on the model. So those geometric structures are called homogeneous. Not only they are locally homogeneous because locally you are identified with the homogeneous space, but here you have this complex Lie group SLN of C, which is the universal cover of the manifold. The monodromy morphism extends from the fundamental group to a group morphism from SLN of C into G in such a way that the image will act with an open orbit in the model. So somehow the universal cover, it will be also a cover of an open set in the model. Give you a right invariant GX structure on the universal cover, and in this way you get a GX structure on SLN of C over gamma. This is an algebraic characterization of what GX structure you can put on SLN of C over gamma. It's purely algebraic. It's exactly those homogeneous spaces which admit a morphism from SLN of C into G, which is transverse to the isotropy H. And for the example of the affine space, if you look to G for the affine space, so if you look to G for the affine space, then you have this morphism from SLN of C into G. And the first step is to say that any group morphism from SLN of C into the affine group can be linearized. So in fact, you will go to the linear part of the group, and any linear action of SLN of C on Cn do not admit open orbits. So the linear actions. So this SLN of C cannot act linearly on Cn with open orbit. Here, sorry. So I'm a little bit. You're right. Sorry. This is it's not the same n. This manifold is of complex dimension n squared minus 1. So for the affine space, I need to look to the affine space of dimension n squared minus 1. So sorry about this. Here, this n is n squared minus 1. And so here, it's n squared minus 1. So this okay, so the group have the same dimension as the linear space. And I'm saying that it's not possible to act with an open orbit. Thank you for the question. So for SL2 is C3. So why somehow this can be considered as a interesting result? For the following question, which is still open, so I will try to advertise for this open question. There is this question, still open. Take a M complex compact manifold and L a holomorphic vector bundle admitting a holomorphic connection, a holomorphic linear connection. Then L admits also a holomorphic flat connection. So this question was asked by several people. There are partial answers. Partial answer, which is positive, is the following. Take M-Kaehler manifold and L, the tangent bundle. And here the answer is yes. If you take a compact Kaehler manifold with a holomorphic affine connection in the tangent bundle, then there is a flat one. The answer is going like this. First, starting with the holomorphic affine connection, you can compute Chern classes of the manifold, the rational Chern classes. They have representatives which will be holomorphic 2K forms. If you compute starting with the holomorphic connection. But the standard way of computing Chern classes is to take Hermitian matrix. If you do the second computation, you will have another representative, which will be a KK form on the manifold. This implies for Kaehler manifolds that the cohomology class is 0, meaning that on Kaehler manifold, admitting holomorphic affine connection implies that all the Chern classes of the bundle vanish. Now, if you assume, moreover, that this is the tangent bundle of the manifold, the first Chern class vanishing implies the existence of Ricci flat metric by Yau's resolution of Calabi conjecture. And the fact that the second Chern class vanish implies, in fact, that the scalar curvature is 0. So in fact, you have a completely flat metric, completely flat Kaehler metric on the manifold. Bieberbach's theorem implies that up to a finite cover, you are a torus. So in fact, holomorphic affine connection in the tangent bundle of a Kaehler manifold implies that you are covered by a torus. Now, this corollary is somehow a counterexample for the question. If you assume that the flat connection here must be torsion-free, I remember that flat torsion-free connections are exactly those which are isomorphic to the standard connection of the standard affine space, meaning that admitting a flat torsion-free connection implies complex affine structure on the manifold, implies you are locally modeled on the complex affine space. Or those polystable manifolds, SLN of C over gamma, of course they admit flat connections because the holomorphic tangent bundle is trivial. So this trivialization of the holomorphic tangent bundle is a flat connection with torsion. The torsion comes from the fact that the group is non-abelian. And this shows that you are not able to put flat torsion-free connections on SLN of C over gamma. But this is not a counterexample to the question, since in the question you allowed your connection to be with torsion. So now I will give you some result toward the direction of this question. Give you two results. If you think the answer is yes, this implies that simply connected manifolds do not admit holomorphic affine connections. This implies, if yes, simply connected manifolds do not admit holomorphic affine connections. Because if you are simply connected, and if you admit a connection, if yes, you will admit a flat connection. Flat connection means that you can trivialize the holomorphic tangent bundle because you are simply connected, and the parallel transport gives you complete trivialization of the holomorphic tangent bundle on a simply connected manifold with flat connection. But trivialization of the tangent bundle means you are a quotient of a complex Lie group by a lattice. You are a G over gamma. So the fundamental group is gamma, in fact. There is no compact, complex, simply connected Lie group. You don't have complex example as the sphere, S3, or things like that. So if yes, simply connected manifolds do not admit holomorphic affine connection. So I will give you two results in this direction. But I don't have this. I have less general results. The first result is a theorem with Ben McKay, which says that simply connected manifolds, here M is complex, compact manifold, simply connected and with algebraic dimension 0, do not admit holomorphic affine connections. There are lots of interesting manifolds of algebraic dimension 0 admitting holomorphic affine connection, but they have infinite fundamental group. For example, deformations of SL2 of C over gamma. They admit holomorphic affine connections. They admit even holomorphic Riemannian metric coming from the Killing quadratic form, but they, of course, they admit infinite fundamental group. Here, this hypothesis could be removed, but we are not able to do it now. The second result, going into this direction, is a joint work with Indranil, showing if you have compact manifold, which is simply connected, and algebraic dimension 1, then M do not admit holomorphic Riemannian metrics. Once again, here there are many interesting examples of manifolds with holomorphic Riemannian metrics and algebraic dimension 1, but they have infinite fundamental group. So let me give you some hints about how one can go to this kind of result to prove this. So let me focus first on the first statement. Are there any questions about the statement? Somehow you need to want to prove that those manifolds do not admit holomorphic affine connections. And the first step of the proof is to show that if they admit some connection, the connection will be very symmetric. So the first step of the proof is the following. In fact, the first step of the proof works for any rigid holomorphic geometric structure. So, step 1, you assume that your manifold is simply connected with algebraic dimension 0, then M admits a holomorphic rigid geometric structure if and only if M is toroidal. There exists a C étoile N action on M with a dense orbit, with a dense open orbit. So, among those simply connected manifolds with algebraic dimension 0, those which admit a holomorphic rigid geometric structure are exactly those which are toroidal. Toroidal here is the non-algebraic version of toric manifolds. So here you have C star to the n actions with an open orbit. So you have a open dense orbit in the manifold, which is a quotient of C star to the n by a discrete subgroup, and somehow M is a equivariant compactification of C star, of the C star action. So there are very interesting examples of those manifolds of algebraic dimension 0, for example, on S3 times S3, or coming from the Calabi-Ekman complex structure. And this if and only if comes from the fact that we prove that this action is a rigid geometric structure. This action gives you a holomorphic trivialization of the tangent bundle on an open dense set. This holomorphic trivialization on the open dense set is obviously a rigid geometric structure, is a connection, but even in the neighborhood of points where the action is not of maximal rank, we are able to prove that preserving those vector fields implies that you preserve some affine structure, and in fact, this action is rigid, also always rigid. So how one can prove this toroidal structure? This comes from Bogomolov theorem. Once again, we use the fact that we are of algebraic dimension 0 in order to prove that there exist local Killing fields acting with a dense open orbit. Now, we use the fact that we are simply connected and a theorem of Nomizu, which enables us to extend the Killing field. So this theorem of Nomizu is a very nice result. It was proved by Nomizu for real analytic Riemannian metrics. It's about Killing fields. It's about symmetries for real analytic Riemannian metric, saying that you can always extend along a curve Killing fields for real analytic Riemannian metric or real analytic pseudo-Riemannian metric. Of course, this result is not true for C-infinite things. imagine this is the flat metric. Take a translation. It's a killing field. But then you make a bump here, and this killing field will not extend through this bump because it extends as a killing field, as a vector field, but it does not preserve this. But of course, you cannot do this in a real analytic setting. If you are flat on an open dense set, you are flat on that. And this is, in fact, interesting and very different. Real analytic geometric structures will be much more rigid than smooth ones. And Nomizu's theorem enables one to extend killing fields along curves. And if you are simply connected, this extension is univaluated. So if you have a small symmetry of a rigid geometric structure and your space is simply connected, in fact, this small symmetry extends in a globally defined vector field. Meaning that here on these manifolds, you have lots of globally defined vector fields, which moreover preserve the rigid geometric structure. Now, why those vector fields will commute? How do you get this abelian action? So you look to this A, which is the Lie algebra of those vector fields. Preserving the geometric structure. Nomizu's theorems say that A acts transitively on an open dense set. But why A is abelian? And this is what we call Gromov abelianization trick. The idea is to put in the geometric structure those extra killing fields. So you produce a second, you start with those are killing for a rigid geometric structure G, then you produce an extra geometric structure by putting together G with a basis of vector fields, preserving G. You put them together. Now, Bogomolov theorem is still true because you are on algebraic dimension 0, and Nomizu's theorem is still true. Meaning the symmetries of G prime also are globally defined and transitive on an open dense set. So if you look to A prime, those vector fields, which are killing, those vector fields commute with all x, y, meaning in fact that A prime is in fact lies in the centralizer of A. And A prime acts transitively on an open dense set. So doing this, you get now an abelian algebra commuting holomorphic vector fields, preserving the geometric structure, and with a little bit of more work, you see that this comes from an action of C star to the n. Now, the second step of the proof is to show that now you have lots of symmetries for your holomorphic rigid geometric structure. And the second step of the proof step 2 is to show that if nabla is A invariant, that implies that A also preserves a flat torsion-free affine connection. Meaning that we use the symmetry of our connection to show that we can modify the connection in a flat torsion-free affine connection. Now you have this developing map going from the universal cover of the manifold, which is the manifold because we are simply connected, into the affine space. This developing map must be a local diffeomorphism, which is a contradiction, because our manifold is compact. So this gives the proof of the fact that those simply connected manifolds with algebraic dimension 0 do not admit holomorphic affine connection. And I finished my time. I will also say that with Indranil, we do the same for manifolds with algebraic dimension 1, because Bogomolov theorem can be adapted. So when you are of algebraic dimension 0, you have lots of symmetry. They act transitively on an open-dense set. When you are of algebraic dimension p, you still have symmetries acting with orbits of dimension n minus p. So if you have a manifold of algebraic dimension 1, you still have a foliation, which generically is a foliation of dimension n minus 1, where the symmetries act transitively on the leaves of the foliation. And we use this foliation to show that those manifolds cannot admit holomorphic Riemannian matrix. So the idea here is that those rigid holomorphic geometric structures on compact manifolds are very special, and one can try to classify them. And this is an attempt to introduce in complex geometry tools from the differential geometry, because interesting examples are in the non-Kaehler situation. Usually, theorems are known to be true, like this classification of holomorphic affine connection on Kaehler manifolds. They are known to be true with hard proofs. They use Yau theorem and things like this. And here we try to introduce tools from the differential geometry to study non-Kaehler manifolds, which admits holomorphic geometric structure. Thank you. Yeah. I mean, of course, if you allowed singularities for like meromorphic sections, you will have lots of them, and you cannot hope to get this kind of local symmetry for your tensors. And I think there is no hope to have a classification of those. There are many of them. Oh yeah, this could be very interesting. Now, so this will be different way of studying those objects. So this is very rigid. Your examples are much more flexible. So maybe what will be interesting in your example is to understand the singular locus and characteristic classes properties around this singular locus. Like generalizing for those tensors what is known for foliations, like Bombot formulas and things like this. It's much more flexible, so I think the idea it would be to study in this direction. Yeah. Okay, interesting question. There is this stabilization conjecture to say that you take any, even in the real setting, you take any compact manifold, you take a product by a torus, with big dimension maybe, then it will admit an affine structure. So this is, and this is known to be true under some hypothesis maybe. So your question is in the same direction. You allowed yourself to add trivial vector field, trivial line bundles. Do we admit a holomorphic? Mm-hmm. Mm-hmm. Okay. 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 I understand. Mm-hmm. 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 I understand. It's reasonable. I don't know, but good question. Yeah, I didn't think to the question. Yeah, very interesting. I don't know if it's false. Yeah. Mm-hmm.